Hello everyone. Today I'm going to present my research on performance analysis of electric vehicle battery thermal management system. I am Ravin Dhakal and currently doing my PhD in mechanical engineering from Texas Tech University. Here is the outline of my today's presentation. I will first talking about the background stuff regarding the battery thermal management system and talk about modeling of battery thermal management system using MATLAB and Simulink, and also discuss about what are the modeling condition I have used for the BTMS simulation, and we'll discuss about the simulation result and then validation of the result using some experimental data and talk about discussion in conclusion. Let's discuss about why battery thermal management system is essential. We can say electric vehicle have been so widely used and there is high demand for longer life, battery life and higher power output from the battery. So most of the research nowadays focus on the battery life and higher power output from the battery. Therefore, battery thermal management system is essential to be able to transfer heat away from the battery packs as they are charged and discharged at high rate. So during the vehicle operation, it is like charge and discharge at high rates. And also, heat generated by the battery when you use can pose safety threats to the passenger as well. So this is an extreme condition of the battery, and we can see while companies like Tesla, BMW, Toyota can use a traditional liquid cooling for their indirect cooling system, but there is a continued research and development on BTMS system to advance the electric vehicle safety. This graph through the increasing sales of electric vehicle in the world, and we can see that in US as well from 2016, from 2014 to 20, it like rapidly increases. The sales of electric vehicle increases. We can see in world about like 2 million electric vehicle sales in the year 2020, and while talking about US alone, we can see about 600,000 electric vehicles since a year 2020. So it increases rapidly nowadays. So that's why the battery thermal management system is very essential, and research and development on it is also very essential. So to get most out of the battery, it is really important to keep an eye on its operating condition, especially temperature, which has been shown to have a direct impact on battery performance and life. So that's why BTMS is very important in control of thermal behavior of the battery. That's why a good system simulation tool can minimize the time and cost of designing such a complicated thermal management system. That's why we need promising simulation tool, which would be like very easier for designing the BTMS. A simulation model also need to be able to easily synchronize with simulation program of the vehicle and be useful in accessing different control strategies. So that's why in this study, we built and simulated a more general and popular battery thermal management system using MATLAB and Simulink. Well, let's talk about modeling of battery thermal management system. We can see this uh, equation, which typically consists of cooling, heating, insulation, and ventilating, which basically follows the conversation of the energy equation. So this is a conversion of energy equation, conservation of energy equation. Because chemical interaction in cell are complicated and heat generation is difficult to anticipate, these kinds of chemistry like charge, discharge profile, construction, ambient temperature, and state of charge play a very vital role. So this can be expressed with the equation, the second equation, which is shown there. This is a diagram which consists of a typical battery thermal management system, which we have developed using Simscape Fluid Toolbox of MATLAB Simulink. And here we configure the system input, that is drive cycle or charge cycle. We took FTP75 drive cycle as our input, and we can see the heating and cooling unit as well here. And it consists of like three branches to switch operating modes, that is heat and cool the battery. And we can see the battery pack on the top of cold plate with cooling channels to direct the cooling liquid flow below the battery pack. So this is an schematic diagram and also a MATLAB and Simulink model which we have prepared on MATLAB. And let's discuss each unit separately. Here we have a battery pack subsystem in the Simulink. We use like four packs of battery, each having at temperature T1, T2, T3, and T4. And we can get these values of the temperature in the battery using the Simulink model. And this is a cold plate subsystem in the Simulink model. Here we can see the heat transfer and temperature at each cold plate. We can see the lines consists which gives like temperature and heat generated at each cooling plate. This cooling plate is used to cool the battery packs. And here we have heating and cooling subsystem in the Simulink model, which consists of refrigeration system, radiator, and heater. And we can get the temperature of all these three systems. Using the model, we can configure the system inputs, charge cycles, and plot the performance measures such as heat flow rate and mechanical output and input of the system. By using the Simscape Interactive Result Explorer, we can visualize and analyze every detail in each block of the battery thermal management system. Moreover, we can generate a reusable code to change the input and output from the model, which helps to develop our own model. Here, the system simulation is performed using FTP75 drive cycle, which is a federally approved drive cycle where the vehicles runs at different velocity, speed, and for a certain time period, which will encounter different scenario of temperature inside the battery. So in the United States, the federal test procedure FT75 is widely used for the environmental certification and fuel efficiency testing of light-duty vehicles. And we can see the parameter here. We have used 31 ampere hour lithium ion cells, and the mass of the battery is about 250 kilogram. And the battery specific heat capacity is 795 joule per kg Kelvin, and the total vehicle mass is about 1700 kg, including the passenger. So this is our modeling input condition of the simulation. And this is what we got in our simulation result. We can see the vehicle speed, battery pack temperature, power, pump power, and refrigeration power in kilowatt in the graph. So we can see the temperature inside each pack of the battery, which is in the limit of 10 maximum temperature and minimum temperature, while the vehicle speed goes up, or maybe after some time the temperature inside the battery pack gradually increases, but within the limit. So it follows the limit which would not exceed the temperature difference between each pack should not exceed more than 5 degrees Celsius. That's why we can see from the plot that it doesn't exceed the 5 degrees Celsius limit. So we can get really good results from our simulation. And we can also see the pump power and refrigeration power in the plot as well. And this is the result where we can see the heat generated by the battery pack, and all the battery packs have same amount of approximately same amount of heat generation. And then we can see the heat flow rate inside the coolant, and then also contribution of the cooling branches like refrigeration system and the radiator system. And another graph on the right side is about the current, voltage, state of charge, and temperature inside the battery pack. How the current, voltage, and state of charge and temperature like are related. So we can see here as well the temperature inside the battery. All the battery pack are almost similar, and which doesn't increase that much, which is below the limit. The temperature difference between each battery pack is less than 5 degrees Celsius. So this is a simulation result which we validate using different experimental data found in the publication. The MATLAB Simulink model of battery thermal management system used in this study is validated using the experimental data provided by the battery developer. This is the one validation criteria. And another one is experimental data of 31 ampere hour lithium-ion battery from Cookman manufacturer consists of current voltage, state of charge, and temperature at a difference time of FTP 75. This is provided from the manufacturer. And the another one, we can also validate this result in the experimental data that can be found in the research work of Tarun et al. We have provided this reference link on our reference section of the presentation as well. So we can see during driving behavior, battery starting temperature and ambient temperature influence the battery thermal management system. And different driving cycle can change the battery thermal management system feature in hot weather, but may less significantly in the cold weather. So it varies in cold and hot region. The ambient temperature was the most relevant variable because it affects the BTMS system. The battery initial temperature, which represent the preconditioning treatment, had a significant, substantial impact on the energy usage, particularly in extreme hot and cold temperature. And also, we can see that detailed thermal and CFT analysis is essential to get the deeper insight of the temperature inside each cell, because we can see the overall temperature of the cell, but if we want to see the temperature inside the each cell and see the presence of hot spot inside the cell, we need to do the detailed thermal and CFT analysis. So here are some of the reference which we have used, and we have used this Cookman, that is a manufacturer from the battery, and we have also used some of the MATLAB Simulink resources, and for the validation purpose as well, we can see these references. Thank you very much, everyone, for listening to my presentation. If you have any question, please let me know. Thank you, my PI, Professor Siva Parmeswaram, for providing an excellent opportunity to present my work in this conference and also working in his project. Thank you very much, everyone.